In this video, we will first learn about some more reactions, most of which relate to aromatic rings. And then we will talk about multi-step synthesis, which is the process of doing multiple reactions in a row and getting to a product. Importantly, what we're going to talk about is retrosynthesis, which is the design of those synthetic pathways given an end goal in mind. All right, so the first two reactions we're going to look at are reactions that are intended to be useful because they take ketones and reduce them into alkanes. So the Clemens reduction is the first one of these. Here's an example of a Clemens-Sen reduction. All Clemens-Sen reductions will look like this, where there's a zinc amalgam species, so that's this zinc-mercury mixture, and that is serving as a source of electrons, overall allowing you to get to the product where it looks like the carbonyl oxygen here is just replaced by two hydrogens. The mechanism for this reaction is not really understood, so we're not going to look into it. These reaction conditions will actually work pretty well for aryl alkyl ketones, but not as well for ketones where the two groups are both alkyl groups. In that case, what chemists have found is that by using a mixture of zinc dust and hydrous acid, or acid without any water in it, then you're able to reduce dialkyl ketones into just alkanes. A second possibility is to do what's called a Wolff-Kishner reduction. So again, the reaction is the same. It's taking a ketone, reducing it down into an alkane here. The way this works is a little bit different in terms of the fact that this is now a reaction operating under basic conditions. So the Clemens-Sen reduction is acidic, the Wolff-Kishner reduction is basic. These reaction conditions are actually pretty versatile, so they will reduce carbonyls in almost any carbonyl-containing functional group down to 2 CH bonds. Chemists have been able to deduce a mechanism for this reaction, so we'll go through that now. The first step involves a reaction between the ketone and the other reactant, which is hydrazine. The hydrazine reacts to form a hydrazone, so that's this functional group right here. The mechanism for this process looks just like imine formation from the reaction between a ketone and a primary amine. So if you're not sure how this works, definitely go through and work that out yourself. Once we are at that stage, then what we can do is use a base to deprotonate one of the hydrogens that are on this terminal NH2 group here. That gets us to a delocalized negative charge here that we can envision as being either localized on nitrogen or carbon in our two different resonance forms. Once we have that, then what we can do is to do a second deprotonation. That gets us to the kind of an anion here. That anion is actually relatively unstable and pretty reactive because it can do an elimination like so. That gets us to a leaving group. So actually this whole piece right here is our leaving group, and a molecule of N2 is generated as a byproduct. This carbanion then should be relatively basic, and we have some of our protonated base from before that we can then go ahead and deprotonate. That's our second hydrogen source. That gets us to the product. So again, these are two different ways of reducing a ketone into an alkane. The reason this reaction is pretty important for people thinking about aromatic chemistry is that it's relatively easy to make aryl ketones by doing Friedel-Crafts acylation. And if you recall, Friedel-Crafts alkylation was not a good reaction because it was hard to control. So the way to put an alkyl group onto an aromatic ring is to actually first do a Friedel-Crafts acylation and then do either a Clemens-Sen or Wolff-Kishner reduction to get to the alkane. If you're trying to decide which of these two reactions to use, the key consideration is whether you have something in the rest of your molecule that's going to be affected by acid or base. Right? So if it was not stable to base, then I would choose Clemens-Sen reduction. If it was not stable to acid, then I would choose the Wolff-Kishner reduction. A second valuable reaction is what's called a side chain oxidation, and this is achieved using potassium permanganate. This looks like so, where kind of any alkyl group directly attached to a benzene ring can just be oxidized fully. We're going to assume that we're applying a lot of heat to this reaction using potassium permanganate in water. The mechanism for this is not fully known, but people have been able to detect that there are free radicals present. And so one hypothetical way this could work might be like this, where we would expect some sort of hydrogen abstraction to take place, thus leaving us with this free radical and this other manganese byproduct, which can then undergo kind of another reaction and eventually somehow get us to what's proposed to be this type of a manganese ester intermediate. So you can kind of see where you're getting that first carbon-oxygen bond built in. But from there, the details are a little bit more murky. Again, the idea is that maybe we're generating free radicals here, but the proof is hard to provide. So we're more interested in what this reaction does rather than its mechanism. And one of the interesting quirks of this reaction is that it can actually cut carbon-carbon bonds. So if I take something that looks like this here, and I react it with potassium permanganate and water and heat, what I end up getting as products are actually this dicarboxylic acid and a byproduct that looks maybe like this, but I have a question mark here because this can kind of decompose, and we're not going to worry about that. The majority of the time when we're doing this reaction, what we're interested in is the aromatic side of the reaction. And so what we can think of is that our reaction is cutting at those positions and oxidizing this carbon and also the carbon on the other side as much as possible. So this should remind you a little bit of some of the features of ozonolysis. That being said, it's not an indiscriminate reaction. Because the first step is most likely hydrogen abstraction, the presence of a benzylic CH bond is required for this reaction to take place. So for example, if I take terputylbenzene and try to react it with potassium permanganate, I don't get any oxidation at all. Putting this all together, if you have an alkyl benzene, then you can use potassium permanganate to oxidize that first benzylic carbon all the way up into a carboxylic acid, which makes it a really nice reactive handle to be able to perform future carbonyl reactions. Another very useful reaction is the nitro reduction. It turns out that nitro groups can be reduced into amines just by reacting it under palladium over carbon and H2 gas. The reason this reaction is very useful is because aryl amines are important for making aryl diazoniums, which are then very important for making many other types of aromatic compounds. And so what you find in the literature and in the industry is that this synthetic sequence that I'm showing you here is very common. People will do a nitration to put on a nitro group, reduce it into an amine, diazetize it to get to the diazonium, and then do some sort of substitution onto the diazonium. A fourth important reaction is actually one that we have talked about already, but it's something that we didn't detail, which is that EAS sulfonation is a reversible process. And so, for example, if I take benzene sulfonic acid and I heat it in the presence of sulfuric acid and water, I'll actually get benzene back out as a product. So, of course, not all EAS reactions appear to be reversible, so sulfonation is a little bit unique there. We're not going to worry about why that is, but just acknowledge that it does do that. And it turns out that in terms of managing this equilibrium, the right way to do this is to either remove the water from the product side if you're trying to make the sulfonic acid, or just heat up the reaction a lot if you're trying to desulfonate and remove a sulfonic acid. Now let's switch gears and talk about synthesis. So in this slide, I'm going to give you a little bit of just background information. It's not something you necessarily need to write down, but I want to make the point that for a synthetic chemist, the synthesis and the design of a synthesis is a huge component of the job. There are many molecules in this world that we know are very useful for whatever reason. They might be really great pharmaceutical drugs, they might be great sunscreens, they might be really nice colorful dyes, or they might be really good at moving electrons around in your OLED screens. Whatever the case is, we know there are certain structures that are very valuable, and so it's up to the synthetic chemist to figure out how to make those. So I have an example of this process for a common molecule, aspirin, the painkiller. So believe it or not, around 40,000 or more tons of aspirin is consumed every year, keeping people hopefully a little bit free of pain and reducing heart attack risk. So the question should be, well, if there's 40,000 tons of it being consumed, where is this coming from? It turns out that aspirin It was first synthesized in 1853, and it's a derivative of salicylic acid, which is naturally produced by the willow tree. So this is salicylic acid. Synthetic chemists back in the 1850s then did a carbonyl substitution reaction using acetyl chloride here and the phenolic OH group as a nucleophile that produces aspirin. Since then, the industrial method has evolved a bit and improved a bit, but the general scheme is the same. We're starting with salicylic acid, reacting with an electrophile, getting us to aspirin. So then, of course, the question should be, well, do we harvest all of the salicylic acid from willow trees? And the answer is no. It's not very practical to try to harvest 40,000 tons of salicylic acid from willow trees every year. So then, how do we get there? Well, we have to make the salicylic acid. The way it's made industrially is to start with phenol, which is this molecule here, and go through what's called the Kolbe-Schmidt process. The Kolbe-Schmidt process looks like this. You take phenol, we depronate it with sodium hydroxide to make phenoxide, or sodium phenoxide, and then that is subjected to an EAS reaction with molecules of CO2. That EAS reaction takes place ortho to the phenoxide group here, getting you to salicylic acid. And this reaction is done on over 60,000 ton scale every year. And you can see where this is going, but naturally the question should be, well, and the answer to that is a little bit simpler. Phenol can be synthesized from benzene, and it also can just be harvested from the earth. And actually it turns out that both phenol and benzene are extracted from coal tar. And I think this is an interesting point because it's easy to forget that the vast majority of pharmaceuticals are actually derived from petroleum resources, and so it's something that's very hard to get rid of. Of course, many researchers are working on ways to make these important feedstocks like benzene and phenol from non-petroleum resources, but currently it's financially, at least, the most reasonable place to get these. All right, now let's talk about the process of synthesis and retrosynthesis. So synthesis refers to that forward process. So starting from phenol, I do the Kolbe-Schmidt process here, then I do the acetylation to get me to the final product that I want. Retrosynthesis, often we think about it as retrosynthetic analysis because it's a technique for planning out or figuring out how you're going to do this forward process. And the way you do this is to deconstruct your target molecule. So you kind of go into it saying, I know that I need this structure. How do I break this apart to get to something that I can buy or find very easily? You'll notice that I used a different looking arrow right here, and so this is intentional. This is a retrosynthetic arrow, and it's supposed to indicate that you're doing a retrosynthetic analysis. In other words, you are thinking backwards when you're going from this molecule to that one, and you're supposed to be trying to fill in the synthetic steps that would then take you from the right side to the left. The way retrosynthesis works is you're supposed to identify bonds to break, and to break those bonds to yield what are called synthons, and that those synthons are then going to be related to what are called synthetic equivalents that you know how to make using other chemical reactions. And eventually you're getting to synthetic equivalents that you can either buy from a chemical supplier, or you can make very easily using known methods. All right, let's perform retrosynthetic analysis on aspirin. So the way I would go about this is to look at this molecule and look for pieces that I can buy and other pieces that are then cut off from that piece that I can buy. So if I'm looking at this, I kind of see that I have this phenol right here, and so I'm kind of recognizing, well, I know I can obtain phenol very easily, so maybe that's a good place to think from. And if I'm deconstructing that way, then necessarily I would like to break that carbon-oxygen bond and this carbon-carbon bond. So then in my analysis, what I've come up with is this situation. So I'm going to draw a benzene ring here. And going back to my broken bonds, I need to break those in a direction. And so I would look at this and say, well, I know carbonyls are pretty electrophilic, and they're often undergoing reactions in which they are the electrophile. So I'm going to break this bond in this direction, put the pair of electrons onto the oxygen. For the other bond here, kind of same idea. This looks like an electrophilic carbon, so I'm going to move the pair of electrons in the bond to the benzene ring. So what I end up with is a synthon that looks like that, and that. And separately from that, I should have a fragment that looks like this, and a fragment that looks like that. So these are my 3 synthons. I'm going to say that this synthon should be easy to get to from the synthetic equivalent of phenol. The upper synthon should be just any carbonyl with a leaving group on it. So I'm going to come up with a couple examples here. Something like that. The last synthon then is what I might think of as coming from CO2. Because this is a nice way to have an electrophilic carbon already having 2 oxygens on it. And after this process is when I could go through and say, well, now that I have my synthons, what are the specific reactions that I need to do, and what order do I need to do those reactions in to actually get to the product? So I would start with phenol, and I would explore, do I want to do the reaction with this as an electrophile first, or do I want to do the reaction with this as an electrophile first? And it turns out if you try it, you can technically get it to work both ways, but doing it the way that's done industrially up here is a much better way of doing it because you have a much better nucleophile for this CO2 step, which is a little bit unusual as an EAS reaction. All right, let's try this retrosynthetic analysis on a molecule here. So I'm showing you this propylbenzene that's been nitrated. And let's say I want to make that from benzene. So I would say I'm just kind of going into this telling you that I want to start with benzene and somehow get there. So if that's the case, then I should be able to do a retrosynthetic analysis and say, well, clearly my bond is going to be there and there that I'm cutting. I know it's usually easier to do EAS reactions than NAS reactions, so I'm going to think about my synthons and bond cleavage happening this way, so that I'm doing 2 EAS reactions. That gets me to these synthons. Right here. I know where the benzene is coming in. That's just going to be the equivalent, synthetic equivalent of this synthon. I know how to do nitration and make this nitronium ion from HNO3. And I think I know how to make this alkyl carbocation here, right, from that chloroalkane. Right, through a Friedel-Crafts alkylation, then I can imagine getting maybe to here and to there. So we have a small problem here, which is that we talked about how Friedel-Crafts alkylation is not a very good reaction. And that's where knowing that you can do Clemmensen and Wolff-Kishner reductions becomes very useful. So with that in mind, I would say that maybe my synthetic equivalent should actually be the acid chloride, because I know that Friedel-Crafts acylation is a much more reasonable reaction. And then after the acylation, I can do the Wolff-Kishner reduction to get to product. So that means I've come up with 3 reactions, right? I need to do a nitration at some point, I need to do a Friedel-Crafts acylation, and a reduction of the ketone. At this point, I think I have all the reactions that I need, so then I need to go through and check the order in which I need to do those reactions. So with aromatic rings, it's important to think about directing group effects. So if you look at the 2 groups here, those are oriented para to each other. And so what that means is I can't put the nitro group on first, because this group would direct any subsequent reaction to take place meta. So I have to put on the alkyl group, and it makes sense because an alkyl group directs para. So I need to build that alkyl group first. So I could do that, of course, by starting with benzene, doing a Friedel-Crafts acylation reaction, getting me to the aryl ketone there. At this point, there's nothing preventing me from either the Wolff-Kishner or Clemmensen reduction, so I'm just going to arbitrarily choose the Wolff-Kishner reduction. That gets me to the alkane. And of course, then I can do my nitration. Getting me to the product that I need. So if I had tried to run the reaction at this point, so the nitration at this point, then we would expect our product to be the incorrect product, which had the nitro group meta to the ketone, and it wouldn't make any sense because I could, even if I did my reduction, I wouldn't get to the product that I want. So of course, I'm sure you can appreciate that this is a relatively simple retrosynthetic analysis. And these can get very complicated because the more steps there are, the more conflicting factors there are. And it becomes very important to start to recognize all the different kind of cross conflicts that can happen between given reaction conditions and other functional groups that might or might not be present. In this video, we went over just a few miscellaneous reactions involving aromatic compounds. Those, along with the EAS reactions, NAS reactions, and diazonium reactions, put together a really large toolbox of reactions that can be used to build the vast majority of aromatic compounds that are needed in this world. After learning all those reactions, then we now have just looked at the process of retrosynthetic analysis for figuring out a potential synthetic pathway to make a given molecule.